Okay. Here's a chemical reaction. Here's the K value. And here are some starting product concentrations and starting reactant concentrations. And we want to know if we put all of these chemicals into a container and this reaction begins to proceed. Again, it could be going to the right or heading to the left, but we want to know in which direction will it proceed given the concentrations that we have here. All right. Let's see. Alyssa, J. Sarah, what do you think? How are we going to approach this problem?
I would say start by writing out just the equilibrium stuff. Like
okay, good. What is it?
Yeah. All right, so it would be concentration of Ag squared, and then plus H2S, concentration of H2S.
Multiplied by, right? Mm-hmm.
Yeah, multiplied.
Good.
That is over concentration of H plus squared.
Okay, good. So now, how's that going to help us?
So we can use that to find, so they tell us, they give us all the starting concentrations, so we can figure out Q.
Okay, very good. So we got 2 molar silver nitrate. So how does that, what does that value go?
I don't know. Do we need that, or does that?
Well,
so
yeah, go ahead.
Would that just be the Ag plus? We use that.
That's right. That's right. Because when you put silver nitrate into solution, it releases the silver ion. So that's going to be 2 here, 2 squared. All right, that's this one here. What about the H2S concentration?
That is 0.1
molar. 0.1. Okay. Now, do we have any information about the H plus ion?
They give us HNO3. Can we use that?
Yeah, why can we use that?
I guess we can.
Why can we? Why can we? How do we know we can? Do you remember what kind of chemical HNO3 is?
Yes, it is a weak acid.
Oh, it's a strong acid. It's a strong acid. H2S is a weak acid, right? But HNO3 is a strong acid. Therefore, the concentration of HNO3 is going to be equal to the concentration of H plus ion when we put it into solution. All right. So what does that mean? What is our current Q? What's our current Q equal to?
So that would be 0.4 over 4, which is 0.1.
All right, 0.1. Are we at equilibrium, or do we need to shift towards the reactant side more, or do we need to shift towards the product side more?
So we need to shift to the reactant side more, because at equilibrium, K is a lot smaller.
Yeah. So right now, currently, we're at 0.1, but K needs to be at 5.88 times 10 to the minus 32. All right. So to get a lot smaller, this reaction is going to shift to the what? The right or to the left?
Shift to the left.
And which answer is right? Is it to the left because Q is less than K, or to the left because Q is greater than K?
Because Q is greater than K.
Okay, excellent. All right. Yeah, go ahead, Jace.
So A is like represents the equilibrium constant, and I know Q represents like the current constant. But what is the actual term for that?
The Q?
Yeah, like what is that like?
Q stands for the quotient. The quotient.
Quotient.
Which a quotient is just the answer to this state, to any division statement, right? Fraction problem, right? So you have a numerator and a denominator, right? And the quotient is the answer to that. Good question. Okay. Yeah. So we've been working with problems now that are kind of straightforward in terms of the math, and that's just kind of get our feet wet to get us used to these situations. But math problems can get pretty messy once we begin to square 2 minus x, for example, or 3 plus x, or 0.05 minus 2x. Once we take those values and begin to need to square them, then we get into a little bit deeper math. And we can do that, that's not bad, but it turns out that sometimes we can save ourselves a lot of time by recognizing kind of how small a given shift might actually be. So when I talk about a given shift, if we go back to this problem, in this problem, the x value ended up being 1.91. So it was really large compared to the 2 here. But that was because the k value was so very large. If the k value is really small, then it's possible that the shift will be very small as well. And if the shift is very small, then we can take advantage of that fact and simplify our math. All right? And we'll use some examples here in the future of that. But basically what we're saying here, that in a binomial term like 2 minus x, if x is very small, like 0.00001, 2 minus x essentially is equal to 2, right? So you can simplify problems like that when x is really small, okay? And usually it's when the value of the k is about 3 orders of magnitudes smaller than the constant that we're subtracting, that the shift is taking the value from. So if this value is 2, for example, but my k value is 1 times 10 to the minus 7, then the shift is going to be very small relative to the concentration of the constant. So let's look at an example. Here's a chemical reaction, and we have a k value. And we're going to place 2 atmospheres of A into the container, and we want to know what will the pressure of B be when we reach equilibrium. All right, 2 atmospheres, that's in concentration, or in units of pressure, right? And we can deal with just pressure because we have been given a Kp, where, again, this is the equilibrium constant with respect to pressure. Okay? Well, we can look at our chemical reaction and think about what our reaction quotient is. It's the concentration of our, where did this come from? I don't think that's supposed to be in there. This shouldn't say concentration of N2O4. This should say concentration of B. Let me fix this real quick. That's why I can't fix it, because it won't allow me upgraded versions of this. Okay. So if I write the equilibrium expression for this, then equilibrium expression is going to be not the molar concentration, but the pressure of B over the pressure of, pressure of A squared And at equilibrium, that's going to equal 3.5 times 10 to the minus 16. Okay? If I have 2 atmospheres of A in the container to start off with, what is the pressure of B going to be when we reach equilibrium? Okay? Well, what is the pressure of B to start off with initially? Who can help me out? Jace, can you help me out with this one?
Yeah.
What's my pressure of B initially? If I want to start writing my ice table for this reaction, what's my pressure of B to start off with?
Wait. So we're so is it gonna? Oh, okay. Is it gonna be 1.4 times 10 to the negative 16?
In terms of what? The initial concentration, initial pressure of B?
Yeah.
Well, all I'm asking is, in this problem, it says, here's the reaction, here's the Kp, and we place 0.2 atmospheres of A into the container. How much B do we start with in the container? Does it say anything about that?
No.
It doesn't.
I just thought.
So essentially what we're seeing is that we have no B to start with, and we're starting with 0.2 atmospheres of A. So that is the I for our ice table. So C, the change. What do you think, Sarah? How is this reaction going to change? Do we know if it's going to shift to the right or to the left?
I'm not sure if it will shift to the right or to the left.
Well, if we have this reaction that's at equilibrium and there's no B in the product side, does that mean that there's any way we can get more A?
No, there's not. So I guess it'll have to shift to the right.
That's right. It has to shift to the right. So what am I going to put down here in terms of X? That's what we're using for our shift. Underneath the A and underneath the B.
So A will be minus 2x.
Okay, we have to lose some X over from A to create. And then here is going to be what?
Plus x.
Plus X. Very good. So the equilibrium concentration, what do you think, Camille? How do I identify what the equilibrium concentration of A will be from this information?
Is it like, would it be like 0.02 minus 2x?
That's right. And then this one over here?
Just x.
Just X. Very good. So once we get that done, and you know, if we wanted to be technical about it, we could have thought about solving for our Q and seeing that Q equals 0. And so again, recognizing we have to shift to the right. But once we have these equilibrium concentrations here, we can put these equilibrium concentrations into our equilibrium statement. So the equilibrium statement, B over A squared, I'm going to write that over here, B over A squared. but I'm just going to write it in terms of equilibrium concentrations. So B at equilibrium is going to equal X, and A at equilibrium is going to equal 0.2 minus 2X. Whoops. Oh, no, that's right. But I have to write A squared. All right. And what is this supposed to equal to, Alyssa?
3.5 times 10 to the negative 16.
Very good. Okay, if you have any questions about how we got this statement here, now's the time to ask. Okay, so we got this statement, and we're going to solve for x, which is our shift, and from that x, we should be able to find out, because x is going to be equal to the concentration of B at equilibrium, so we should be able to find out what the concentration of B is going to be. All right, now, how do we solve this mathematically? 0.2 times 2 minus x. 0.2 minus 2x squared. 0.2 minus 2x. Remember how to solve this business? It's a polynomial, right? With FOIL, 0.2 times 0.2, 0.04. Is that right? That's right, right? Yep. 0.2 times 2. Oh, let's see. That was our first outside. Yeah, 0.2 times a negative 2x, so negative 0.4x. We do that again here. Negative inside, right? Negative 0.4x. And then the end here, minus 4x squared. All right. Again, all of that is under x, and all of that is equal to 3.5 times 10 to the minus 16. So, what do you call that? Jace, what do we call that? And it's just a 4-letter word. What do you call it? Yeah, here it is. A mess. That's right. It's a mess. Nobody wants to go through this sort of math, right? So if there's a way to simplify our lives, then we would like to simplify it. How can we simplify this? Well, we said that because this is so small, 3.5 times 10 to the minus 16, then the shift of it shifting towards the product side is going to be pretty small as well. And so if x is going to be pretty small, and we're taking 0.2 and subtracting 2 of a really small number, because this 10 to the minus 16 is many orders of magnitude away from basically 10 to the minus 1 here, right? 15 orders of magnitude away, we can just drop this 2x component completely and leave behind 3.5 times 10 to the minus 16 being equal to x over 0.2 squared. All right, so we dropped our x value there. Now, we could have gone on and solved it and get the same value that we're going to get in the end. But this is a way that we can have confidence we can drop it and save ourselves a lot of heartache, right? All right, so basically 3.5 times 10 to the minus 16 times the 0.04, right? 0.2 times 0.2, 0.04 times 3.5 times 10 to the minus 16, all right, equals 1.4 times 10 to the minus 17. And that is what our x value will equal to. 1.4 times 10 to the minus 17. And that will be our concentration of B once equilibrium is reached. All right. So Here is another problem like that. 1.8 times 10 to the minus 5 is our equilibrium. We start with 3 molar of our acetic acid, and we want to know what will the equilibrium concentration of this acetate ion be. What will the equilibrium concentration of the acetate ion be? Whose turn is it? Sarah, can you help me out with this? What do we do here?
Yes. Okay, so I'm going to start with Q. So, let's see, I'm not sure.
All right. What would, when you say start off with Q, what were you writing, or what are you thinking about writing?
I was just going to write the concentration of C2H3O2 I guess that's over concentration of HC2H3O2.
Now, we have one more product, don't we?
Yes. That's H3O.
Okay. Now, the only reason why we really need to know the current Q is to determine which way this reaction is going to shift, right?
Yes.
Can you tell which way the reaction is going to shift if we put our current values in there?
So, let's see. Quickly. Three. I'm sorry, my brain's not working.
All right.
So,
Well, I think one of the frustrating things is we don't see any information about these products, right?
yeah.
So it's hard maybe to think about it in terms of solving for this Q. It doesn't have to be hard. We could just say, okay, the concentration of this stuff is 0, concentration of this stuff is 0, concentration of the stuff on the bottom is 0.3, and then we could solve for Q, right? That would be just 0, right?
Yeah.
So then what would that mean in terms of our why do we do that initially? What are we trying to do?
So we're trying to figure out which way the equilibrium shifts.
That's right. Which way is it going to shift?
So Q is larger than K. So it's going to shift to the right.
Yeah,
Or no.
that's right. It's got to shift towards the product side, right? Now, be careful about trying to memorize Q larger than K or K larger than Q. All we really have to recognize here is that they only gave us reactants and there's no products. So we know the reaction can't go to the left. It has to go to the right. Does that make sense, Sarah?
Yeah, that makes sense.
Okay, so then I'm going to write my chemical reaction here. HC2H3O2 going to, I don't need to include the water, H3O plus, and C2H3O2 minus. My initial concentration. What's my initial concentration for this, Sarah?
0.3.
0.3. Very good. Initial concentrations of these two?
0.
0. All right. The change?
So that change would be minus X.
Mm-hmm.
Those changes would be plus X.
Very good. The equilibrium concentration here is what?
0.3 minus X. And then X and X.
Okay, very good. So, how can I identify what the equilibrium concentration of this stuff will be? That's what they're asking me to do. How do I find out what that is?
So, I guess we know that it would be x times x.
Very good. So we're basically filling in our equilibrium statement with our equilibrium expressions down here, right? X times x over
0.3 minus x.
Very good. And that whole thing is equal to?
So that is x squared. Or
Yep. X squared over, or what do you want to do here? What do I set this equal to right here?
oh right, 1.8 times 10 to the negative fifth.
Okay. Very good. Now what can I do?
And then I think we can just say that is 0.3, right?
That's right. Because 10 to the minus 5, this is 10 to the minus 1. That's more than 3 orders of magnitude away. So we can drop this value there. And then just do 1.8 times 10 to the minus 5 times 0.3. Set that equal to x squared. So then I can take the square root of both sides. And x will equal 1.8 times 10 to the minus 5 times 0.3, and then the square root of that product. Okay. All right. 0.0023. Is that one of our answers there? Okay. Very good. So again, we took our initial concentration of our reactants. We knew it had to shift to the right because there were no products to start with. We had a K value, 1.8 times 10 to the minus 5. We set ourselves up an ice table, an ice box. Where's my ice box? There it is. Set up our ice box, identified the shift using the stoichiometry of the equation, took our equilibrium expression concentrations and put them into the overall equilibrium expression, and solved mathematically for x. And that was our equilibrium concentration of our product, or the acetate ion, which they were asking. Okay, so let me introduce you to one concept here, and I'll show you one thing. Well, actually, I don't think I'm going to take time to do that. There is, I'll show it to you really fast. But in our calculators, or modern calculators like this, we have solvers that can be used to solve quadratic equations. Some of you also have been in math relatively recent enough, or you were taught a beautiful song that helps you remember how to solve quadratic equations, right? Negative b minus 4ac. I don't know. Anybody remember that song? Anybody want to volunteer?
I remember that.
Oh, you do? Wonderful. You want to tell us really quick?
Well, the one for the quadratic equation is negative b. Oh wait, no, it's x equals negative b plus or minus the square of b squared minus 4ac all over 2a.
Very good. Very good. So if you have that tool in your memory, that's wonderful, and you can use it when you feel that you need to. In this class, essentially, we'll always have scenarios where we don't need to use that because we'll be able to recognize what x we can drop. If that song ever leaves your brain, then we can go to our math menu here. And the last option in the math menu, I get there by going all the way down to the bottom, or just going to the top and then going up one, is the solver. And then once you have the solver here, you can write in a given equation. So for this here, it looks like the equation that we want to write in is 4 x squared minus, no, plus, not minus, plus 4.5. X is achieved by clicking on this button here, 4.5x minus 0.675. So there I have my equation that I've written into my solver, and I can push enter. And what the computer here does, the calculator, it will take whatever value I've given it, and it will put it in for x there and find out what y would equal if it's going to do all the math that I've told it to do. And if that value, I put in whatever value I want to here, and then it chooses a value that's slightly larger, and it looks to see if the new y value that comes out is higher or lower. If it's higher, then it knows, nope, that's not the correct answer. It needs to go down, right? Because the minimum of these graphs are the answers. And so it'll then choose a value that was slightly lower than our initial guess, we kind of call it, this x value. And it'll keep going until it finds a minimum, and when it finds a minimum, it'll tell us what that minimum is here. So I can put in my first guess, and then I can say solve, which is this green button right here, so I need to go second enter, and then it will spit out a number to me, 0.134. Now, because it's a quadratic, I know that there are two regions where this value will cross the x-axis, and that's what we're asking it to do here, solving it, setting it equal to 0, right? So we know that there's two values where it will cross the x-axis, not always, but often. And so it'll give me one of those values, 0.134. And if I wanted to get the other one, I could go in here and change the bounds. Right now, basically, the bounds are from negative infinity to positive infinity. All right? But if I wanted to change the bounds, if I thought maybe there's another bound, right now I have it at 0.134. I don't know if the other one is negative or positive, but I'll try to find out here. Maybe I'll set the bound here at the positive high bound to 0.1. All right, and then I go back up to, this value here, and then I put an answer which has to be between these two bounds. So I'll put in 0.09, and then I'll push solve again, and it will spit out a second value on the other side of the boundary. So we had 0.1 and negative 1.25, 1.26. So that's it. What I've provided for you here is a tool that you can use throughout your scientific life to solve any quadratic that you might need to. And maybe you've been exposed to this in previous classes as well. Well, that wraps up chapter 15, and we don't have a lot of time to go into chapter 16. So I think this is where we're going to stop. But we will start chapter 16 next class, and then chapter 16 and chapter 17 kind of go together. So we won't be having an exam after chapter 16. We're going to have our next exam after chapter 17. Okay? Other than that, I think we're done.